It represents what's happening with the law of large numbers. And what you have here is a x-axis, that is the number of rolls. I'll tell you, it's rolling a six-sided dice 2,000 times. And each calculation here, this is the number 200, so you guys, I know it's hard to see the scale. And this is the relative frequency. Again, relative frequency is success over total based on your experiment, and probability is also kind of success over total. So we're looking at success over total, and I really only want to focus on the first 200 rolls. It's from here, that part of the graph there. Looking at 0 to 200, because you can kind of see it evens out past 200, especially after this value here of 600, it definitely kind of evens out over there. So we see what happens at the end over there. And then we'll look at 0 to 200. What's happening at 0 to 200, I sit there and I roll a dice. And when I roll the dice, it's going to land on one of the sides. It's either going to land on the 1, the 2, the 3, the 4, the 5, or the 6. What happens is I can calculate my relative frequency on rolling a 6. So I can sit here and roll the dice. I'm either going to roll the 6 or I'm roll the 1. Is this 1? Is that what I was talking about? Yeah. I'm either going to roll the 1 or I'm not going to roll the 1. So let's say I roll the dice. It comes up at 2. So the probability or my relative frequency on my first roll of dice is 0 successes out of 1 trial, or out of 1 total. I roll it again. I got the 2 again. My success, which is rolling 1, is now 0 out of 2. So my probability at this point is 0%. Do we agree? 0 divided by 2. And I keep going and going and going. And each time, after every roll of the dice, I calculate a new relative frequency. For example, let's pretend I roll again, and I rolled a 1 that time. Then I have 1 out of 3 attempts. That's my new relative frequency. I roll it again. Hey, I got a 1 again. Well, that goes to 2 out of 4. Now that probability is 50%, isn't it? You guys agree with that? And I keep going and going and going and going. And that's what this graph is a chart of. How many 1s I rolled out of how many rolls. And what happens is, from 0 to 200, I'm working my way to that theoretical probability. Because again, what do we call theoretical probability? It's what's supposed to happen. Think about it this way. How many sides are there on the dice? 6 sides. How many sides of them are 1? 1. That means I should roll the 1 out of 6 times. Right? And I think you guys have covered that kind of probability in other classes. Is that right? Or it's kind of intuitive anyway if you haven't covered it correctly. So the law of large numbers says as we increase these number of trials, I've increased the total, my relative frequency will approach that theoretical probability. And the theoretical probability in this problem is 1/6. Should make sense. And you can see that that probability matches up. Okay? And that's what the law of large numbers says. It says as you repeat those trials, that relative frequency of actual events will get closer and closer to that true probability. To illustrate the point, actually, we do have some time today. I want to go ahead and, actually, no, I'm going to skip this. We don't. We'll come back to it if we do have time within class. We were working on this one. Theoretical probability. Suppose there are a group of 3 girls and 2 boys. Your statistics professor will randomly select 2 students. What is the probability that both the selected students are girls? Okay? Probability that both selected students are girls. A lot of you guys, for this, because again, we're introing this probability, we are looking at, you can get it on your own. There's kind of 2 ways to look at it. We're going to say this. The way I envision it, there's 5 people in my magical bucket over there. 3 of them are girls and 2 of them are boys. What's the probability that both selected students are girls? I look at it this way. We can make a sample space. The way that I look at it is this. Probability that both students are girls. What's the probability right now that I reach into that bucket and pull out a girl? That's 3 out of 5 and 2 out of 5. What do you guys like better, 3 out of 5 or 2 out of 5?
3 out of 5.
3 out of 5. Why? How many girls are in there?
3.
3. So the chances are, if there's 5 people in the bucket, there's 3 chances out of those 5 chances that are reaching to pull out a girl. So I'm going to say first selection or first pull. Does that make sense? My first selection or my first pull is 3 out of 5. Next up, and this is kind of a key to thinking about probability. I reach into that bucket, and I happen to pull out a girl. Yay for me. That's what I wanted to have happen, right? We don't know if I did pull out a girl or I didn't pull out a girl, but we're going to pretend for the purposes of this problem, because it wants them, what, both to be girls? So doesn't that mean the first one must be a girl? And we know that that's not going to happen all the time. It's going to happen 3/5 of the time. Agreed? So I've now reached into my bucket. I've pulled out a girl. Here she is right now, right next to me here. Now, we're looking at our second pull. What's the probability now that I'm going to get a girl the second time?
50%.
A lot of you guys said it. That's correct. It's going to be 2 out of 4. That's right. Now, one key vocabulary word that I want to talk about here is, bless you. That's not the vocabulary. The key vocabulary word I want to talk about here is non-replacement. Replacement versus non-replacement. You've seen that in sampling show up a little bit. You're going to see it in probability here. This case, we have non-replacement. I can't throw that girl back into the bucket because I can't select the same girl twice in order to get 2 girls. Does that make sense? Okay. So realize this is non-replacement. I've got these 2 probabilities, and you're saying, great, Mr. Wood, I understand what's happening here. But this problem says, what's the probability that both of them selected? I got the first one and the second one. Here's the deal. In this situation, we have what's called independent events. And we're going to talk about independence a little bit more today. But when we have independent events, and you need to have both of them happen, I'm going to write "and" there. And I want to connect to what we did last Tuesday. Hopefully you remember this. "And" is an intersection, right? What's the probability that Tyreek makes his free throw and DeMarcus Cousins makes his free throw? Do you remember that was that shaded part that was both? What's the probability that I reach in and get a girl the first time and the probability that I reach in and get a girl the second time? That's also an intersection. What you do when you're looking for the intersection of independent events is you multiply those probabilities together. Okay? You multiply those probabilities together. So this will be 3/5 times 2/4. And some of you guys already knew that. I think you might have had a homework assignment problem on it. We can reduce here, and that will give us 3 out of 10.
And if it's like an OR situation.
An OR situation is looking at a union. It's going to kind of, a lot of these problems are going to come into, let's isolate what the question's asking. And for now, let's keep that as multiplying for independent, okay? Are we okay with that answer of 3/10? Okay. The other thing I want to look at is the next problem. What's the probability that both selected students are boys? How are we going to do that? How are we going to do that? 2 out of 5 times 1 out of 4. Does that make sense? Okay. So 1/10 of the time we're going to get both boys. Now here's my next question. Are those 2 events in the first problem and the second problem, are those complementary events? No? Well, ish. Can't be complementary-ish. Because the idea of complement, it's either this or it's not that. That's a complement. So either both girls are your both not girls. That's not truly the complement. You're either both girls or you're not both girls. Does that make sense? Because there's two things that can happen here that are both not girls. You can have a girl and a boy, or you can have a boy-boy. And we've only covered the boy-boy situation. Okay? Now, what's the probability that at least one of the students is girls? At least one of the students is girls. Well, let's use a little bit. What kind of situations can happen here? We can have a girl and a boy. Will that work? Can I figure out the probability of getting a girl and then a boy? So I'm going to write that down. I'm going to kind of go on another screen here. And we've got, here's my magical bucket. We've got 5 people in there. 2 of them are girls, 3 of them are girls, and 2 of them are boys, right? And now we want the probability that at least one is a girl. At least one is a girl. Somebody said, well, I can have that be boy and then a girl. Would that represent at least one being a girl? Can I calculate that probability of getting a boy first and a girl second? Won't that be 2 out of 5 times 3 out of 4? Do you guys agree with me for that? Yes? Okay. We'll come to that in a second. That's going to come to that. What do we got? 3/10 there? Somebody said, Vanessa said, well, what if I go girl, then boy? Will that satisfy that condition? Okay. Well, what's the probability that I go girl and then boy? Wouldn't that be 3 out of 5 and 2 out of 4? That's the same number, isn't it? It should make sense that those two probabilities come out to be 3/10 both times. Because the same thing's happening. I get a girl and a boy. One I pull the boy first, and then the girl. And the other one I pull the girl first, and then the boy. Probability is the same because I start with the bucket, the same with 5 people in it every time. Probability at least one of the students is a girl. I could also have a girl and a girl. Where do you know that probability? Didn't we calculate that like the first part? Girl, girl. Is that 3/10 also? That's kind of weird. Well, I have these 3 probabilities here. Add them. Multiply them. Okay? This is now an OR situation. So I want to talk about OR versus the AND. I said AND, we're going to talk about keeping it multiplied. Is everybody okay with that AND for independent and multiplied? This is an OR situation. At least one of the groups is a girl. That means I can pick a boy and then a girl, or I can pick a girl and then a boy, or I can pick a girl and a girl. All 3 of those situations satisfy this condition, doesn't it? And if all 3 of those situations satisfy, then each one of those probabilities is allowed to happen. When they're each allowed to happen, or this, or this, or that, that's an addition. So boy, girl happens 3/10 of the time. Girl, boy happens 3/10 of the time. Girl, girl happens 3/10 of the time. For a total of 9/10. Or, theoretically, 9 times out of 10, I will at least get one girl when I reach into that bucket and pull out people. Does that make sense? Now, do you agree that this represents every condition except for boy, boy? Does that represent every condition except for boy, boy? So you're telling me that the only other thing that can happen here is boy boy. Well, you calculated boy. What was that? 1/10. You mean all of these conditions added together will be 10/10, which is 1? You mean I said you always sum all those probabilities can happen in any kind of way, shape, or form? Well, also one that should make sense. 90% of the time, you're going to get a girl, at least one girl. 10% of the time, you're going to get both boys. This and this are complementary ideas. That should make sense to you. That means if I thought critically about this problem, instead of showing you a long way, which I did because I wanted to kind of show you how the OR works, what is the probability that at least one of the students is a girl? I can solve this problem saying that's 1 minus the probability that they're both boys. Or 1 minus 1/10, which is oh me, oh my, 9/10. I am shocked to see that I can get that same answer 2 different ways using solid statistical reasoning. Do we see how that kind of clicks together? What's the probability that students are not the same gender? We kind of answered that already. How many people already have that answer? Not the same gender? Not the same gender. That happens here or here. Those are the only places. It's either girl, girl, boy, girl, or girl, boy. Not the same gender. You should have, or it should make sense to you, that is 6 out of 10, which you will reduce to make it, what, 3 out of 5. I think probability is kind of easy if you are good at critical thinking and kind of see how this stuff fits together. If you're somebody who likes to memorize facts, probability tends to be pretty difficult. Next up. A mutual fund company offers its customers several different funds: a money market fund, 3 different bonds funds, 2 stock funds, and a balanced fund. Among customers who own shares in just one fund, the percentages of customers are followed in the different funds. So this is just a list of data. This is people who own stuff. And I think I have it on this page here. I think this one's easier. What is the probability a selected individual owns a balanced fund? Yes, ladies and gentlemen, it is 7%. There will be some questions like this that are that easy. As I told you before, when probability is easy, keep it easy. We're going to get to some hard probability problems. When we get there, they'll take some time. 7% there. Next one, probably an individual owns a bond fund. We have 3 kind of bonds. Yep. We've got the short-term bond, the intermediate-term bond, the long-term bond, and the James bond. No. Our bonds come out to be, what, 30%? What's probably a selected individual does not own shares in a stock fund? Not stock. 2 ways to do that. You can add up. Ooh, that was cool. 2 ways to do it. You can add up all the things that are not stock, or the way I would do this is I would go 1 minus the stocks and use the idea of complementary events. It's just less numbers to add up. Instead of adding 20 plus 15 plus 10 plus 5 plus 7, No, I actually, honestly, I'd rather see 0.3. But in this case, since it started in percents, I'll take both. Very rarely will I mark down in that case. I will mark down more for rounding errors than I will on that difference right there. Stocks, so that would be 1 minus, what do we got? 0.18 plus 0.25. Said I think that one's easier than the other problem we did with the boy, girl, and the girl, boy. Our next,
Is that an AP test question?
this? No. There are some that are that easy. Maybe 1, 2. But I will cover the AP test. Actually, is 40 multiple choice questions with your calculator for an hour and a half, and then 6 free response questions with your calculator for an hour and a half. Of those 6 questions, 5 are, you guys have already seen them, some of them. Those frappies that I attached, we haven't gone over them much. Those frappies are actual AP questions. Hopefully, you're gonna when I'm giving you those frappies, you're gonna see if those problems, based on what we covered, aren't that hard. Now, I haven't covered them and gone over like how to answer them and scoring and anything like that. We'll handle that like later on in the term. All I want you to see is that the 5 AP free response questions, you guys have already seen a good 6 or 7 of them. You know what I'm saying? I've only shown you ones of things we've covered so far in class. But those 5 free response questions aren't usually that difficult. Hopefully you feel that way when you look at them. And you're not just saying, well, man, I don't know how to do this at all. And the nice thing about the free response is there's nice partial credit. And if you get a 2 out of 4 on them, that's still doing pretty good. And I'll show you how that works later. For now, I just want to keep working on it. And the 40 multiple choice is very similar to the multiple choice questions that you see on your tests in this class. I try to model and pick multiple choice questions that are very similar to format and wording and level of difficulty of the AP free response. AP multiple choice. All right, here's the deal. Our next topic is what's called expected value. And I'm going to make this deal to class. You've got to pay me $50 right now. And here's what I will give you for your $50. You get to roll that dice, this dice right here, wherever I put it. Where did I put my dice? You get to roll this dice. So basically, I'm going to hand you this dice. It's going to cost you $50. And when you roll the dice, if you roll a 1, 2, or 3, I'm going to give you $100. Which is a profit for you of what? $50. Do we agree with that? Okay. You roll a 4 or a 5, I'm going to give you $25. How much did you lose? $25. Now, bad news. If you rolled a 6, you're going to pay me how much? Another $50. How much did you lose there? $100. Now my question to you is, do you want to play my game? No, because Mr. Wood always cheats and he's good at statistics and I'm not, and therefore I don't want to play his game, because he wouldn't make a game where I'm going to win. Not a gambler. If you were a gambler, I can't say that word. If you were a gambler or pretended you were, I want to know statistically, is this a good game for you to play or not, and why? And that's what I'm more concerned about here. And it's going to come around what is called expected value. And expected value is the value of things over time. It's going to tie into the law of large numbers. The expected value is the value over time. Again, I think most of you guys, how many people do understand the scenario and what I'm asking? You got to give me $50, you roll the dice, and then I'm either going to pay you more money or you're going to pay me money, right? Okay? That's the premise of the game. And I think you'll also agree with me that you're going to, some of you guys will roll the 1, 2, and 3. In fact, if everybody in class played this game, wouldn't most of you guys roll the 1, 2, or 3? Because do you also agree with me, half this class theoretically should be winners? Does that make sense? Based on theoretical probability, half of you guys will be winners. And then the other half of you guys will be either a little bit of a loser or a big loser or a complete loser. That doesn't sound right. Don't take that out of context. In the principles of this game, you would either lose a little or lose a lot. Does that make sense? So again, it now becomes, statistically speaking, Is it worth it to play the game or not? And I think if you can follow this thought through, if I were to play this game a large number of times and I win more than I would lose, then I should play the game a lot. Does that make sense? And if I play the game a lot and lose a lot, well, I shouldn't play. Right? Does that make sense? I mean, that's kind of basic common sense as far as game playing goes. So, how do we do that statistically? It's this right here. We're going to kind of create, not kind of, we are going to create some value here. You guys have already told me 50% of the time I'm going to be a winner. How do we get that 50% of the time? Hopefully, it was, well, Mr. Wood, a 1, 2, or 3, I win $100. Does that make sense? 1, 2, 3, I win $100. Well, there's 3 opportunities out of 6, success over total, relative frequency. So 3 out of 6, and are you okay with me putting just our profit and loss at this point? Because we agree here I'm going to actually just win $50. Does that make sense? So if you roll a 1, 2, or 3 in the context of this problem, you're really going to win $50. Does that make sense? Is everybody kind of okay? Yeah?
Right. So if you need to win, you don't take the $50 trade?
Well, I said I'm going to give you $100. If you roll a 1, 2, or 3, you're going to get $100. Like, everybody's going to give me a $50 bill to start this game, and I'm going to give you the dice. You're going to roll it. If you happen to be one of those individuals that rolls a 1, 2, or 3, I'm going to give you a $100 bill back. But really, that means it's called a net. You paid 50, got 100. You netted $50. You won, or it's positive 50, which is why I'm putting positive 50 here instead of 100. So do we agree that this represents my frequency, which is how often it's going to happen, and then my profit from when it's going to happen. 50% of the time, or half of the class is going to get $50. Is that okay? The next event or the next situation we have here, which happens 2/6 of the time, that's a 4 or 5, you're going to win $25. So 2/6 of the time, you're going to win $25. But did you really win $25? What did you net? It cost you 50, you won 25. You actually, so I'm going to write a negative 25 there. And hopefully you know why I'm writing a negative 25 on that one. And lastly, if you roll the dreaded 6, you are the biggest loser, which means you get exemption for that week. You're actually going to lose $50. 100. Yeah, thank you. Whew. I didn't write that right. Have I kind of painted a picture about the goods and bads of this situation? And have I equated some probabilities with each one that hopefully fits within the context of this problem? How often it's going to happen, the frequency, with the amount that I'm going to win or lose. Okay? So now I'm giving value to it. 3/6 of the time, I'm going to get $50. What I'm going to do is multiply those values here, and that's going to tell me how much I'm expected to win. 3/6 of the time at $50. Half of 50, that comes out to be, I think, $25. I'm going to multiply these two together. What's 1/3 of 25? I don't know. Negative 50 over 6. I don't know. What is it? 5.5? 12.5? Negative, right? Negative 12.5. Oops. And 1/6 of the time I'm going to lose $100. And hopefully you agree that's not going to happen very often. Which you'll negative 8.3.
Yeah, because it's 50 divided by 6, not by.
50 divided by, it should be negative 50 divided by 6.
Yeah,
What do we got there? What'd you say it was?
8.3.
8.33. And 100 divided by 6 is going to be what, 18 something? No. 16? 16.66. All right. Do you agree that this is an or situation? You're going to roll a 1, 2, or 3. You're going to roll a 4 or a 5. Or you're going to roll a 6. So you're going to win this, or this, or this. To find my expected value over the long run, if I play this game over and over and over and over and over again, my expected value for me, the student, would be this, or this, or this. What am I going to do with those values? I'm going to add them up. Well, 25 plus negative 8.33 plus negative 16.66 basically sums to 0. Or negative 0.01 because of rounding issues. Okay? So this is what's called a zero-sum game. It means I'm not going to make any, me the teacher now, I'm not going to make money off you guys, but I'm not going to lose money off you guys in the long run. It also means that you, the student, not going to make money off me in the long run, and you're not going to lose money off of me in the long run. In the long run. The catch is in the long run. If we just played one round right now in class, some of you guys would be losers and some of you guys would be winners. But all I would do, because I know the way the probability works, all I'm going to do is take the money from the losers and pay the winners with it. I'm going to break even. Theoretically. Now, if I gave you guys all trick dice that only rolled 1, 2s, or 3s, then I would be out a lot of money. Wouldn't it? Does that make sense? If I also gave you guys loaded dice and they only rolled 4, 5s, or 6s, maybe that's what I should do. Because then I'll walk away with a lot of money in my pocket and you guys will walk away with not much money in your pockets. Does that make sense? Okay? So, what is this? This is called expected value. It is one of the equations on your formula sheet, those things I gave you a long time ago. It looks weird. This is what the formula looks like. Formula looks like this. It says expected, I think, EX is what it says in your formula sheet. It's actually the letter E. And it is the sum of the probability of X times X. Okay? The sum of the probability of X times X. I believe it's in the top right corner, maybe the third or fourth one down. Do you have the formula sheet out? Third one down on the formula sheet. That is called expected value. And I want to show you how we apply that. Right now it should match, hey, probability of X times the event X. In this case, and you're summing it, remember this sigma symbol means sum in mathematics. Sum to add, not sum of things, some of the things. Sum as in adding them all together. The probability times the outcome. The probability times the outcome. The probability times the outcome. And then here we are. We're summing them together. Okay? Expected value. All right. Here's the next part of the problem. I decided to play this game in class with all of my students, and I got caught by the campus security. And they turned it over to the cops. So here's what happens. Cop tells me this. When I go to jail, half of them stay 1 day, a quarter of them stay 2 days, a fifth of the people who go to jail stay 3 days, and 1 person out of 20 stay 4 days before they're either released back into the population or they're sent to the other jail. So I want to know, because I got caught running this gambling scheme here on campus with students, I probably got fired, but I want to know how long I have to stay in jail. So now you guys calculate that for me. That's what you should have done. And if you did it, you got 1.8 or 1 4/5. Either way. And then I said, hey, if you got 1.8 here, if you got 1.8, if you really wanted to convert that over to hours, remember 0.8 is 8 out of 10. It's the same thing as 4 out of 5. Make it as a ratio problem, x over 24 hours a day. It'll give you how many hours. So 1 day, 19 hours is what I think it came out to be. Something like that. Okay. So, is it worth 2 days to jail and get fired from your job to run a gambling? Probably not. Where I make no money, yes. We make a lot of, well, that's what I said. Like, I have a conversation with students all the time. Mr. Why can't you just give me an A in class? Sure, I can give you an A in class. But when I just start giving away grades, pretty much my integrity is shot, my trustworthiness is shot, my job is shot. I mean, that teacher gives everybody A's, the kids don't know anything, they all actually fail the class. I'm probably going to get fired and not rehired. So if you want me to give you an A, you just need to pay me enough money to allow me to retire because I will never be able to go back to the teaching profession. I'm only good at one thing. Well, no, I'm only marginally good at one thing, and that's teaching. Again, I don't have anything else I can do with my life. So, if you can pay me enough for retire, I tell you what, I live the life of luxury. So, popping collars, I'm gonna go to the thrift shop. What's that?
You can just become Walt.
Oh yeah, I could. Breaking Bad's ending, man. He's done. Have you been watching that whole series?
Well, I'm only on season 3.
It's addicting. It's almost spoiled.
Disney know Gustavo is here.
Hey, can you please find
All right. Next kind of set that we're looking at, and I kind of set it up a little bit yesterday in the worksheets. We're going to be going in a little bit more today. The right-hand side of this you should recognize, because up top, that's an intersection. That says the probability of E and F. The bottom is just the probability of F. Now, what I have on the left, that's different. You guys probably haven't seen anything like that before. This is called a conditional probability. Conditional probability. And what it is that I'm telling you something specific about the problem. On the right-hand side is what we use to calculate it or how we find it. Okay? Remember, and or intersection means both. Are we clear on that? And then this is now a condition. So we'll read that. That reads as find the probability of of E given the condition F. And it's pretty easy to see, and I think some of you guys, if you kind of are seeing how we're calculating these probabilities, it's kind of intuitive. So I'll show you how to use the formula, but I'll also show you how to get it off just a given data set. If you printed up your notes, I don't think my data matches your data. I'm not positive on this, but maybe. Here we go. This data was taken from a while ago. We have way more students than this now. So we got, does it match? Okay, good. Antelope High School data. Hopefully you just see it's a data chart here. We classified students. They can only be in one category. We do have students that are in fine arts and athletics, but we said pick one category. So you see up here, freshmen, sophomores, juniors, seniors. Here, if they're in athletics, if they're in fine arts, which we counted as dance and band and theater for our fine arts, and then I think we also counted yearbook and media for that. And then other, we said, hey, do you use something in the school that's not athletic or not fine arts, and then this is like student government kids or they're active in clubs or something like that. Okay? So that's just a data set representing our student population. Like I said, it's off based on a while ago. And what we're going to do is then take this data set and calculate some probabilities here. First probability I want to look at is the probability of what? Does yours say junior athlete or junior given athlete? Just junior athlete? Okay. So let's go with what's written on your notes then. What your notes say, just that. Is that right? It says junior given athlete. That's what I have. Oh, there's no bar there. Okay, that's fine. So your notes, the bar disappeared on it. If you have the notes, write the bar in your notes there. Because this tells, oh my, I need to recalibrate this book. Probability of junior given, that's the line that says given that you're an athlete. Right? The way that we find this, or we calculate those probabilities, we can look at the raw numbers here. I want the probability that you are a junior and an athlete divided by the probability that you're a junior. Okay? Again, oh no, I set it up wrong. Sorry. Given that you're an athlete. There we go. I wrote the formula down wrong. That's how we find it statistically. That's the straight cut and dry formula. Again, the way I tend to look at probability is try to think about what's happening and what I know. Find the probability that you're a junior if you're an athlete, or given that you're an athlete. Here's the catch. I want to know the probability that you're junior if you're an athlete. I'm not talking about all the students in school here. I'm talking about what students in particular. I'm talking about athletes and juniors. Okay? In particular, for this probability, I want to know the probability that if you're an athlete, what's the probability that you're a junior? Or given that you are an athlete here on campus, what's the probability that you're a junior? So hopefully it makes sense to you that I'm talking about just athletes in this problem. I'm talking about just athletes in this problem. How many athletes do I have in the context of this problem? 600. And I get that by adding the freshman, sophomore, junior, and senior athletes together. 600 athletes. I want to know, of those 600 athletes, how many of them are juniors and athletes. Hopefully, you figure that's 140. So the probability that somebody is a junior, given that they're athlete, is going to be 140 over 600. Okay? Notice what I have up top. Junior and athlete. I have 140 people that are junior and athletes out of 600 athletes. Okay? That's how that formula works. If you wrote it as a overall probability, it'll cancel out. Reduce that, it'll get the probability. I don't know what that number comes to. Point what?
0.23 repeating.
0.23 repeating? Okay.
The 3 is repeating.
Oh, the 3, just 3. Okay. All right, next up. Probably somebody's in fine arts given that they're a sophomore. Think carefully about the condition that's a given. In conditional probabilities, the condition always comes second. So in this case, that will be the probability of fine arts and sophomores divided by the probability that they're a sophomore. We can look at the numbers here, fine arts and sophomores. Fine arts and sophomores, there's 90 of them. That's my intersection. Students are usually better at the intersection. Yes? That's all right. We'll just go with what I got here. It's usually easier for students to find the intersection. Fine arts, sophomores, there's 90 of them. And they get the numerator correct. That's 90. Divided by the probability that their sophomores are divided by sophomores. Where do I find sophomores at? Add up that row there. That's my sophomores there, isn't it? So my sophomores are going to be 160 plus 140, 390. Reduce that, 9 divided by 39, another decimal. I don't know what it is. 2.3?
301. I mean, 08.
There we go. I like that a lot better. What'd you say? There it is. 0.2308. Really? You told me 2.3? And you're saying 0.23 is the same thing? So the probability that somebody is in fine arts and a sophomore is 230%. The same thing, Mr. Wood. If that's how you appreciate percents,
We're both having that.
I want to start banking with you, so that when you're giving me like 3% interest, you're really going to give me 30% or 300% interest. Oh, it's just a decimal point. It's not that big of a deal. Really? The difference between a billion and a million is just a zero. Actually, three? No, it's one. It's one. A million and a billion is 1 0.
Yeah, so then
Right?
you just shift the 1 over.
Yeah, it's a zero. The difference between a billion and a million is a zero.
Okay.
Oh, no, you guys might be right on this.
1 million, 10 million, 100 million.
There's a million.
And a billion.
I think you might be right. This is a
Yeah,
billion.
it's like 1,000 million.
It's three zeros. I was wrong.
Okay, well, 1 million, 10 million.
Don't get me wrong. Yeah, I said I was wrong. I only make 3 mistakes a year, so
You only have 40 minutes.
right. But it's just a decimal, doesn't it? All
Yeah.
right. Now the truth is, if you understand numbers and the difference between a billionaire and a millionaire, the difference between a billionaire and a millionaire. Thanks, you want to make more money. Yeah, really? The difference between a billionaire and a millionaire is a billionaire does not care about $1 million. Really? Because he's got 999 other millions of them.
Then you won't be a billionaire.
Sure. I'm sure if he invests none of that $1 million, he goes and bets it all on black and wins, and then he's back to a billionaire. Yeah, there you go. Let's see. Probability that a freshman and an athlete, given you're an athlete, probability that you're a freshman, given you're an athlete. Once again, we're talking about the athletes. 600 should be 150 over 600 for that one. Okay, if I kind of start skipping these because we're seeing the patterning. Patterning, I can't talk good.
I can't talk good.
I speak better. I are an English major. English be my best subject. Good. That's what I want to talk about. Number 4. Would you just do that on everyone? Did I give you any condition?
No.
Nope. I just want to know if you're in fine arts or not. So this probability is straight up success over total. How many students do we have in the school? How many students are in fine arts? Notice this now becomes this number here divided by that number there. Does that make sense for your probability of fine arts? Okay. All right, I'm not gonna do more of those. This one's harder. I'm gonna play it. What time we get out of class today? What time?
107.
What we got? Oh, good. What we have here is a list of people with insurance. Something you guys are. How many of you guys drive? How many of you guys have to pay for your own insurance? Kind of.
Just 0.
Just 0? If you have just a 0, yeah. If you pay 0 on your auto insurance, you're still your parents are probably paying your auto insurance for you. And usually your parents are like, make sure you keep your grades up. By the way, how many people, we'll get into this later in class. since you guys drive and are dealing with insurance at this point in the ballgame, and you guys are all in AP classes,
Oh, great.
here's the deal. You've probably had this conversation with your parents. I don't know, may not be true. You get a discount on your auto insurance if you have good grades. Because statistically speaking, there's a lower probability of you getting in an accident over time from ages 16 to 21 if you have good grades. In other words, they're correlated. The lower the GPA, the higher the number of accidents you have. The higher the GPA, the fewer the number of accidents you have. Does that mean that's the case for you individually?
No.
No, because some of you guys have already had that happen. Okay? Now, does that also mean if you have a low GPA, you're going to get in a ton of accidents? Also not true. But it does mean if I'm the insurance company that over time, I know that I'm going to win in the long run. That by and large, if you have the higher GPA, you're going to get fewer accidents. And if you have a lower GPA, you're going to get in more accidents. So it should make sense to you. If I'm in a business of making money, and there's all businesses out there are really in business for making money, I want you to be my customer. And I want you to be my customer if you're not going to get in a lot of accidents. So I will give you a cheaper rate so you come to my company if you have high grades. Guys, guess what? Ages 16 to 21, you lost the lottery. You were not a girl. Just by being a guy, you get higher auto insurance. Why? Really? I think we all know the answer to that question.
No, we're the best.
That doesn't mean that girls are perfect drivers and guys are not perfect drivers. It just means that statistically speaking, over time, we're talking tons and tons and tons and tons of teenage drivers that guys have gotten in more accidents than girls. And it may be because girls just don't drive cars that much. Doesn't matter. Whatever it be, if guys are on the road, I think that makes more sense to you too. What's that?
Comment.
I drive
Here's the deal. You've lost the lotto insurance lottery if you are a guy and have a low GPA. You will be paying the most amount of insurance because you have the highest probability of getting in an accident. It's not saying that you individually are going to get an accident or you're not. It's just saying, statistically speaking, over time, that class of drivers has gotten into more accidents. If you're a girl and you have high GPA, you get a break on insurance. Now, here's the deal. Everybody gets their break on insurance if you're a girl with a high GPA until you get in that first accident. And then once you get in that first accident, congratulations, you're with everybody else. If you're the low GPA and guy and you get in your accident, guess what happened to your auto insurance? It went up again, or they say, no thanks, you can go find Geico. They don't even want to deal with you anymore. What's that? And then if you stay at the Holiday Inn, it's a double bonus because, never mind. All right. Meanwhile, back to the problem. We've got two things happening. You guys aren't homeowners yet, but hopefully at some point in your life you will be. You will have to buy homeowners insurance. It's part of owning a home. You're not allowed to own a home without it. And most of you guys are already experiencing the auto insurance deal. How many of you guys have done accidents? I don't know, just a couple of us. Ish. Did your parents make you pay a deductible? Has the deductible come into play yet, you guys? Okay, don't you have a job yet? When you're entering this game, and you guys are going to have to enter the auto insurance game sooner than you're going to enter the home insurance game, they're going to give you this other option. They're going to say, do you want a low deductible, a medium deductible, or a high deductible? And usually students ask, well, what's a deductible? Well, I'm glad you asked that question. A deductible is what happens when you get in an accident or when your home gets broken into. It's how much you have to pay in order to fix things. Okay? If I have a low deductible, that means if I get in an accident, I only have to pay my insurance company $1,000, and they're going to fix whatever happens to my car and the other cars in the accident. I have, let's say, a $30,000 car. I hit a $60,000 car. We've done some damage, and it's my fault. Insurance says, I will take your $1,000, Mr. Wood, and we'll take care of the rest. Kind of a nice situation. That's why you have insurance, by the way. That's a $1,000 deductible. I will have to pay X amount of dollars per month at my $1,000 deductible. What's that? $1,000 deductible is probably a medium, right? If for car insurance, $1,000 is probably medium to low, honestly. Probably medium to low. A high deductible says this: I don't have to pay that much insurance every month, because you pay insurance every month, no matter what. Whether you get in an accident or not, you're paying it. So I send my insurance company a check every month to insure my automobiles. If I don't get it in an accident, I still send them the check. If I choose to have a high deductible, that means if and when I get in an accident, I'm going to pay a lot more than $1,000. I still have the $30,000 car. I still hit the $60,000 car. But this time, since I have a high deductible, I've got to pay my insurance company $5,000 for them to take care of everything. What's that? Well, yeah. What's that?
I said, but do you pay less monthly?
But I pay less per month. Let's say I'm only paying them $100, $50 a month. Okay? $50 a month. $50 a month with a $5,000 deductible. Okay? You want to go to that $1,000 deductible, you're going to pay them $100 a month then. Does that make sense? You pay them $100 a month, that money's going away unless you get in an accident. When you get in an accident, you only have to pay $1,000 instead of $5,000. If you want that low deductible, when I get in an accident, I still have my $30,000 car, I accidentally wrecked the $60,000 car, I don't want to pay a lot of money out of pocket, I have a $500 auto deductible. That's kind of nice. It only costs me $500 to fix everything. But guess what? Students usually say, well, why don't you take that one every time? Well, that one's going to cost me $250 every month, whether I get in an accident or I don't. What's that? Get in an accident once a month. Here's the deal. Usually that's the right answer. Because students say, well, if I only have $500 deductible and I pay $250, I want to get my money's worth, so I'm going to make sure I wreck my car every month, right? Well, here's what happens. They keep you paying $250 a month, but instead of your $500 deductible, it's now $1,000. You keep getting your money's worth, they're going to bump your deductible from $1,000 up to $5,000. You're still paying $250 a month. So the insurance companies are the best statisticians out there because they're in the business of making money off of your mistakes.
Do you pay insurance and deductible, or is the deductible part of your insurance?
You send a check every month for your insurance.
And it includes a deductible?
No. When you get in an accident, let's say you started driving in January, so every month, January, February, March, April, May, June, July, August, you send them a check for $100. They get to keep that money. In August, you get in an accident. Okay? Let's say you have a $1,000 deductible. That means you're going to send your company $1,000, and they'll fix your car and whoever you wreck. Does that make sense?
It's kind of with the assumption that the $100 you've been sending them every month, that's what goes towards paying for the car that you just wrecked.
Right. And what they do, they invest that money and it grows exponentially. There's a whole other cool stuff on the economics of it, in my opinion. I'm a numbers geek. But how they come up with those things is very much why girls pay cheaper and high GPA pay cheaper than guys in low GPAs. If it's not your fault, does your deductible go up? No. But what happens is if you have several accidents that are not your fault, your account will start to be flagged. Even though you don't have to pay your deductible, and if an accident's not your fault, you don't have to pay the deductible, and your insurance rate shouldn't go up. But what they're going to do, let's say you're a 16-year-old male driver with that high GPA, and you've been in 4 accidents over the last 2 years. None of them were your fault. You will probably get a rate increase because they still have to deal with it, even though it's not your fault. your insurance company is going to still deal with it. It's still going to show up on your record. So it depends on your insurance company, and it depends on how long you've been driving. Good things happen when you go, this should make sense statistically to you. Good things happen if you go a long time without making mistakes. So what happens in school, right? You get good grades, you go a long time without making a mistake, you're going to get your straight A's. You drive a long time without getting a speeding ticket or in an accident, as an insurance company, I'm saying, hey, you're an easy customer to have. I love you sending me money every month with me and not having to do any work. I'll cut your rate down, make sure you stay with me as a company. Does that make, I mean, it's in the business of making money. And in the actuality that I actually get in an accident, let's say I've been with this insurance company for 20 years. I've reported an accident at the 19th year or 20th year. They don't really care because of my record. That's the other thing that impacts young drivers. When I've been driving for 20 years, you can look at my driving history and see if it's good or bad. When you're a 16-year-old driver, you're a risk because the insurance company doesn't know if you're a good driver or you're not. So you have to build up that credit or reputation or whatever you want to talk about. And credit scores, how many of you guys have had a conversation about credit scores? I mean, you see it all the time, and credit scores are a big deal. Not having a credit score and not having a credit card hurts you just like being a 16-year-old driver does. If I'm talking about loaning you money and I don't know how good you are at paying back money, you're risky to me. Just like at age 16 as a driver. You may be the best driver out there. You could be racing NASCAR as a, in your free time. I don't know that. You're just as risky as anybody else out there to me until you drive for 5 years and I see that you actually are good. Same thing with credit cards and spending money. You need to take small loans out and repay them in order to establish a credit history so that when you want to buy a car at, say, 19 or 20, you've had all these, I borrowed $500 and I paid it back. I borrowed $200 and paid it back. You're establishing the fact that you can pay back loans. If you establish the fact that you pay back loans, then I would be more inclined to give you a loan for $20,000 versus somebody that's never done it before. And credit history is huge. You guys see it, freecreditreport.com, all that stuff online. It's a big deal, especially since real estate happened and a lot of job loss happened. It's a bigger deal now than it used to be.
So like you said, that if you're like a 16-year-old and you think like you're a big risk, or if you get your drive, or like you get your insurance and you like don't even like drive for a whole year, so they technically think you're a good driver, but you haven't even driven yet.
Yeah, you can play that game.
That's why.
Yeah, you can play that game. I don't know that I personally would play that game because you still have to pay the insurance. Right. You're paying insurance. Like if I'm not driving a car, I don't think I'd want to pay a year of insurance not driving a car.
I'm gonna go here and I'm like 10 minutes away walking distance, so I'm not even gonna drive to school.
Right, but according to the credit company, the insurance company, if you have your license and you have your car and they're insuring you, it means every month you're sending them a check.
Yeah.
Okay? It really means it's going to cost you $1,200 or however much. Usually for, I think, students of your guys' age, it's usually around $100 a month. So you're looking at $1,200 to establish your safe driver for 1 year driving history. And I don't know that you're going to get that big of a break, personally. I would say no insurance and just start driving at 17. Save my $1,200 and maybe instead of paying $100, I got to pay $125 a month. You see what I'm saying? It'll still save me, at that point, maybe $1,000, which put that towards a car.
If you don't drive.
That's, well, yes, obviously, if you don't crash. Everything's predicated on the idea that you don't make a mistake, right? You getting into college is predicated on the idea you make less mistakes than other people. You want to get hired in a job or you want to keep your job, you need to make less mistakes than the people around you. That's what it is.
So say you don't get into an accident for a long time, and you still have to pay the next time.
There's new schemes that are coming out. One of the schemes is a vanishing deductible. I don't know if you've seen that. It's advertised that one of them, Progressive or whatever, is a vanishing deductible. So if you drive with them for 10 years, like every month that goes by with safe driving, they'll knock $5 off your deductible. But I think in order to get a zero deductible,